So now we move on to the next topic, which is on a more technical subject, as far as I am concerned at least. It is on the modern railroad signaling, exploring 20th and 21st century systems in global context. The speaker is Manikandan Venkataramanan, who has been a moderator so far, and so he would be now introduced by Atulya Sinha. Atulya Sinha is a railwayman by profession, but a rail fan by choice. And that is how Atulya Sinha would like to describe himself. Currently, the Chief Administrative Officer of the rail wheel plant of the Indian Railways at Bela in the state of Bihar, he is a mechanical and a production engineer with a postgraduate diploma in management. He has worked in diverse important capacities in various aspects of railway working. Atulya Sinha has a keen interest in railway history and heritage and is a very active member of the Rail Enthusiast Society. And I may also add, having a great knowledge about the literature pertaining to railways across the world. Thank you, and over to you, Atulya.
Atulya? Good evening. Good evening. Am I audible?
Yeah. Yes.
First of all, thank you, Mr. Pandey. Thank you very much for introducing me. And I have the privilege of introducing my good friend, Manikandan Venkataramanan, known as Mani to his friends. I say he's a very good friend, although I have never met him in person, but thanks to social media, we have been interacting, and I consider him a very good friend. Mani is a finance and risk management professional who has obtained his Chartered Financial Analyst and Financial Risk Manager charter. He did his MS in Finance from the University of Pittsburgh, once a railroad town that was the hub of the Pennsylvania Railroad. He currently serves as a senior consultant with one of the big 4 American consulting firms. Mani is an avid rail fan and an active and passionate member of the Rail Enthusiast Society. He is interested in reading about the past and the present of railroading, its operations and technology. He serves as a director of the UK-based WATTRAIN, where he represents India, and he's also a member of the UK-based Advanced Steam Traction Trust, which has as its objective the promotion of the principles for L D Porta for continuing steam locomotive operation. He connects and liaises with various railroad associations in the USA. Today's presentation will be on modern railroad signaling, exploring 20th and 21st century systems in global context. This is a very challenging topic, especially for a person like our friend Mani, who does not have a technical background, nor is he a professional railwayman. But I am sure that he will do justice to the subject. It is intended to provide an overview of modern signaling systems with a focus of signaling for high-speed railway systems and modern freight railways. There will be a summary of the technologies used, regulatory frameworks, impact on safety, efficiency, and sustainability, key challenges, and a brief comparison of the systems used in USA, Germany, France, UK, and India. I can't think of anyone other than Mani who can present on this subject, and I'll not delay his presentation any longer. Mani, floor to you.
Thank you so much, Atulya ji, for such a wonderful and kind introduction. First of all, let me say at the outset that I'm indeed honored to be introduced by you. And thank you so much for the immense faith that you have reposed in me for this topic. And I should also thank all the members of the Rail Enthusiast Society for giving me this opportunity to provide this talk. So in the meantime, let me just share my screen. All right. So at the outset, I know that this is a little bit of a complicated topic, an arcane topic, and I'm not a signal engineer. I don't have a technical background, so let me tell it at the beginning itself. But I have tried to make it as interesting as possible, and I have covered some videos and a lot of pictures. And at the same time, what I have covered here is what developed over the 20th century and what is currently being used in the 21st century and what we can expect in the future. Something that would be relevant for us is the overall theme of this construct. And then, since there are various kinds of signaling systems being adopted all over the world, so what is it that we may focus on? So initially, I thought that we can focus on the history of signaling as it developed from Great Britain. But then my good mentor, Mr. Sanjay Mukherjee, he suggested that I focus on some specific areas so that that would be of interest and relevance for all of us. So what I've covered here is something which is not being applied in India and something which we can easily understand because of the subject matter being in the English language. So basically, I've covered the signaling which is done by the United States, a form of signaling called speed signaling, and then the modern signaling systems in the US, followed by high-speed railway signaling in Germany, with an overview of all that. And I'll lightly touch upon the Indian Kavach. And I think we already had some interesting discussions about centralization by Mr. Jeet Sondi, and then the Vande Bharat speed trials in Kota, Savai Madhopur, and then the dedicated freight corridor by Mr. Rajesh Prasad. So I'll be linking all that when the time comes. And then finally, we'll go to conclusion and future trends, where it's as a result of AI and what we are going, it's nothing but complete automation, which is the future. So starting ahead, we will start off with the first area in the modern signaling, which is the development of modern signaling. So our story here begins from automatic block and the basis for automatic block. And like any signaling system here, the theme or the philosophy for improvement in signaling has always been safety and capacity. Anything else follows safety and capacity. So all the new buzzwords that you see, like efficiency, economy, sustainability, interoperability, they can all be clubbed into these two paradigms, which is safety and capacity. So that's where in the late 18th century, early 19th century, you had the development of automatic block beginning. And beginning with where? It started with the track circuits. So the gentleman that you see on the right, on the top right, is William Robinson. He was responsible for building the first practical, trustworthy, and fail-safe. These are all important terms in signaling. Practical, trustworthy, and fail-safe track circuits. That was invented by him, and it was in the United States, and it was progressively expanded across multiple railway companies and for construction in the US. Of course, you had some track circuits prior to this in the UK, but a practical application was done by him. And this track circuit forms the basis of automatic block signaling. And on your lower right here, you can see an example of a track circuit. So on the track, you have welded joints, and welded joints are linked by wires. And nowadays, you have a lot of adhesives and other materials which are being used to ensure that this stands the test of time and this is not sabotaged as well. All right, this is a very simple diagram that shows how a track circuit works. Due to the wires and the joints which are connected by wires are running on the track forms a closed circuit. And then if there is no metal or a flanged wheel on the track, it signifies that there is nothing on the track, it's clear and the signal indication is clear. And then once the metal wheels flows over the block section covered by this track circuit, what happens is it shunts the circuits and shorts the circuit, resulting in track occupancy, and you get the red signal over here. I know I'm rushing through because there's a lot of material to cover. So I'll probably take around 55 minutes so that we'll have some time at least for questions, and then we can take the rest offline. All right. After the track circuit, what came next? So as I said, the automatic block signaling system worked closely in conjunction with the speed signaling philosophy. So what we adopt in India is called route signaling. Whereas if you look at most of the high-speed railway systems, the freight corridors or high-speed freight systems or whatever is there in North America, they use this philosophy called speed signaling or in conjunction with weak route signaling. They don't use route signaling. So what does this mean? So speed signaling means any signal aspect provides an indication to the driver as to the speed that he or she has to take on the route, either on the divergent route, through the interlocking, through the sidings, to clear the interlocking, whatever. It gives the speed, it doesn't give the direction. Whereas route signaling, on the other hand, gives an indication of the route that has to be taken by the driver, and it doesn't necessarily signify the speed that the loco pilot has to take. This particular philosophy was actually designed by this engineer, signal engineer, which you can see over here. His name is Arthur Holly Rudd. He was supposed to be one of the greatest and the most famous of the signal engineers. He worked for the Pennsylvania Railroad. And at that time, Pennsylvania Railroad was a pioneer in designing a lot of systems, whether it's your locomotive test plans, high efficient, high horsepower steam locomotives, which we covered yesterday, as well as test equipment, test facilities, and of course, signaling as well. So some examples of the speed signaling philosophy that he devised is seen on this extract from a book. This book was presented to me by one of the other members of the Rail Enthusiast Society, Kaushik Darwatkar, who's an expert on electric traction. So I just thought I'll take some examples of signaling from his work, from the book that he gave. So you can see here that this is the speed signaling philosophy which was developed. So each railway company in the US had its own way, slightly different way of dealing with it, but this is the base. So you can see, first of all, the railway companies in the US adopted a 3-position upper quadrant semaphore. They didn't use the 2-position lower quadrant as was generally being adopted in the UK. It was a 3-position upper quadrant. And they combined 2 semaphores on the same mast to multiply the number of aspects that could be generated by a signal. So the aspects are the indications which the signal represents. So to increase, so the philosophy, again, I go back to philosophy, to increase the granularity or the number of aspects to be displayed by a signal, they adopted this approach. So you can see here that if it is vertically up, it is all clear, proceed at normal speed. If it is at an angle over here, it is approach, but be prepared to stop at next signal. And then they also had this concept called speed, which is what we are going to talk about. So this is one of the primary examples of speed signaling. You stop and then you proceed at restricted speed, which forms the basis of the permissive block, which we will see in some time. And then by combining 2 semaphores on the same mast, they were able to say whether they can take a lower speed, a medium speed, but the driver has to stop at the next signal, a block away, or they have to reduce the speed up to a certain level and stop, say, 2 blocks away. So this is one aspect of it. And then the same set of indications were also provided through color lights. And then there were some Midwestern railway companies which used a searchlight signal to adopt the same thing. The last two are a little bit different though. These are what is called as a position light signaling, which was again designed and developed by Arthur Rudd. So what he wanted to do was he wanted to do away with color lights altogether. So whatever position aspect were signified by a semaphore, he wanted to replicate the same, albeit with much more granular indications using color lights. Using lights, just lights, single color light, like a white color agnostic, white color lights. So that's essentially what he tried doing here. The variation of this is what is currently being used by Amtrak in their high-speed rail corridor in the Northeast, so which we will come there shortly. And then some railways started to modify his approach, and then they combined some color light elements to his position light, and then they called it the color position light, so which we won't get into now, otherwise it will become too complex, but we can cover it offline in case you are interested. All right, so how does this speed signaling with automatic block work? So you can either, the basic automatic block is 2 block with 3 indications, but what the American railroads adopted was 3 block with 4 indications or 4 block with 5 indications. Why did they do this? Why do you need 3 block with 4 indications and 4 block with 5 indications? Basically, you have to ensure that you can put more trains on the same track. That's essentially what they want to do. So assume that there are 2 tracks, one up track and down track, and then you want more number of trains on the up track and more number of trains on the down track. If you have a very simple route signaling philosophy, or if you have just a 2-block 3 indication approach, you should have multiple distance signals, as we call it, or approach signals as they called it, which increase the space between the trains, and then it reduce the number of trains which could go and on the same track. So to reduce the space between two trains, they adopted a more indicative approach, 3-block 4 indication or 4-block 5 indication. And how they went about doing this is what is given here. So they mixed and matched, as I said earlier, they had a lot of approach signal, which gave a speed indication to reduce the distance between two trains so that the throughput or the capacity could be increased. Moving on. So what is currently being used in the US? So that's the picture I have on the left-hand side. So it's a current Amtrak Northeast Regional train, and you can see the position light signal. This is indicating stop because it's facing the other way, and there is a train, as you can obviously see. And then what I wanted to show from here is this signals that you are seeing is basically a variant of the signaling which was devised by the Pennsylvania Railroad. And then you have a lot of aspects that are being shown. So currently, with all the latest technology, they are showing 9 aspects in the signal to finely modulate the speed. And then these 9 aspects which they have in the signaling is also replicated in the cab, so that as the speed increases, the response time needed will be more. The driver cannot just rely on the trackside signaling. So he or she would need the similar indication being replicated in the cab so that they can increase the average speed of trains, and also they can reduce the speed and stop and have more efficiency and capacity. So that's another thing which we will cover shortly. But more than the Pennsylvania Railroad, there was another railway which took Arthur Rudd's design, is invention. So that was the Chicago and Northwestern Railway Company, which is currently a part of the Union Pacific Railway over there. So as you can see, I'll just show you the indications. So you can see here that they have 2 semaphores. So what these companies used to do is they had an equivalent light signaling approach, which corresponded to the semaphore. And so you have red over green, which says that you have to proceed not exceeding medium speed. So which is again a speed signal. And then if you see below here, you have red over yellow, you have to proceed at restricted speed. I'm just giving some examples of speed signals here. And then this is red over yellow over here, but there is a slight difference between this and this, right? You are going at restricted speed here with just one yellow indicator, but here you have a much more granular indication. So you have to proceed to stop at the next signal. That's what it indicates, and so on and so forth. I'll just quickly browse through this. So these are just a sample of the multitude of indications you can have from a position light signal. So I just wanted to give you an overview of that. We need not go into details of this because we don't have the time now, but you can see that the railway companies over there, they use not just a circular disc with one dot here. They also use circular discs with a subsidiary indicator. The subsidiary indicator with position light was used for slow speed running, and the circular disc was used for high speed running. And then they mixed and matched everything to give a much more finely tuned view of the signals and the speed which the driver had to take so that they can increase the capacity and the speed. So using this approach, the Pennsylvania Railroad was able to have a train which could travel at an average of 90 miles an hour from the 1920s. And they had in-cab signaling from the 1920s itself. And that's essentially what I wanted to indicate over here. All right. So this is an overview of the speed signaling and automatic block. Associated with the automatic block, of course, is interlocking. So what is signaling without interlocking systems? So the interlocking systems basically help us in setting the right points and direction of the track. And it ensures that there are no conflicting directions. And then the signals are also aligned with the direction. That's what the interlocking basically ensures. And there have been various kinds of interlocking through the ages. So we have pure mechanical interlocking, which you could see in old style signal boxes in the UK. And then you do have electrical interlocking. So the electrical interlocking is what you see in the middle of the image over here, where both the signals and the points are set by electrical pulses, or it could be just the signal and the points could still be electropneumatic. What you see here on the left-hand side, this thing is an electro-pneumatic interlocking system, one of the earliest examples designed by Union Switch and Signal Company in the US. So we will later on see a video of this in some time in this presentation as to how it operated. And nowadays, this is another board. This is another example of electrical interlocking of the kind which was used in Chicago. And I just gave some pictures of this. And then, of course, what is currently being used for interlocking is it's solid state electronics, not even relay. We moved from relay to solid state electronics, and everything is computerized. And it's by a touch of a mouse or even through touch screens. Okay, now this is a small video on an automatic block system at Canadian National Railway's Rockford Division in Illinois. We won't cover the full video, we'll just cover a small section of this. Just give me 1 minute. So what you can see here is that you see a rudimentary speed signaling, which is even applicable for freight railway operations using automatic block, a simple automatic block. So you can see here that how the approach signals and LO signals, which talk about stopping at the next block or two blocks from there, it gets upgraded. So if you have a flashing LO, it means that you stop from 2 blocks from now. And then just a flashing LO without anything else means that it's somewhat clear, and then it becomes green once the dispatcher corrects it. So that's essentially what they are trying to say here. So the speed signaling is also applicable for sidings, for diverging routes. For that also, the signal is set such that the track is cleared for the diverging route, but it will actually tell the speed. But that is taken care of by the dispatcher. Okay, so from here on, the video actually covers one train and what happens to its subsequent traffic, which follows the train as well as this train itself. So we don't have time to cover that now, but we will probably cover it in case we have time later, or maybe I'll share a link to this video. Moving on. The next outcome from the automatic block is the centralized traffic control, which is what uh, the railways progressed to. So what happened in the US was that, as Mr. Jeet Sonti was telling yesterday about the centralization of multiple zones, so that one zone had multiple thousands of route miles under it in China, the American railroads also came to the same conclusion. So their operating divisions all merged together. They merged different regions together so that more authority was given in the hands of a single operating manager. And as a result, even the signaling, more areas of track got combined and it got centralized. And that was also helped by the outcome of miniaturization, electronic circuits. And then due to the technology, a single dispatcher could actually control multiple route miles of track. And then on top of this, you had a different philosophy. Again, the philosophy plays a role here coming in, called as absolute permissive block. This photo here is one of the largest centralized dispatching centers in the world. I think this covers around 15,000 route miles of track of the Union Pacific, which is under the CTC network. And this is called as the Harriman Dispatching Center, which is completely under CTC under modern technology. Okay, what is absolute permissive block? So this concept was devised by the competitor to Union Switch and Signal, the General Railway Signal Company. This became the basis for centralized traffic control. So you had a combination of both absolute and permissive block system. So stop and proceed. So where did stop come? The signals at the end were absolute, and the signals in passing sidings became permissive. And there were a lot of overlap protections which were provided. And then what they used here was that they had multiple crossover sidings. And then what that enabled is something which we will eventually see. So what happened was they ensured that on the same track, you will have bidirectional running. So as a result, a train need not be restricted to one direction, either up direction in the up track and down direction in the down track. They can go in both the directions to increase the throughput and capacity. That is what this technology ensured. So we will see that in subsequent slides. So this is a paper from a magazine called Signal Engineer, which spoke about the benefits of absolute permissive block. I mean, we are not going to go into the specifics of that now, but we will cover it at the end in case we do have the time. Let me see. Let me just proceed. All right. So now all this was set in place to develop CTC. So CTC ensures that all signaling is remotely controlled and centrally across the network, and it ensures complete centralization. So in the US, you have both BNSF and the UP, where there is only one dispatch center which controls signaling for its entire network. And the dispatcher there has control over the direction, train control, and safety. And you have both the interlocking and signaling, which is automatically ensured. And here are some videos as to CTC in action. As I said, so what does CTC ensure is that it ensures that on the single track, you do have that bidirectional running, and it's called as two-main track. And then what US Railways found out was that if you just have an automatic block with two tracks and on the one hand, and you have a single track on the other hand, 70% of the traffic which was handled by that system could be handled effectively on a single track with this technology. And then as a result, there were some railroads which moved completely to single track from double track, where they could handle it, where they saw that this would mean, because they were going through rough periods of bankruptcy and so on and so forth. To cut the cost, they did it, and they were successful also. They made it profitable. Okay, the video at the top talks about CTC as it was in the 1970s, and the video at the bottom is a shorter video, but it talks about the CTC as it is currently. So let's see what it is here. This also covers a model railway where they have recreated it. So basically, this is the United States as of the 1970s, and then they have recreated that electro-pneumatic uh, interlocking with CTC board. And then we are going to see how the signals change when the dispatcher changes the routes as well as the signal on the CTC board. Okay, so this is how a dispatcher used to work. So you have a track board over here, which indicates the occupancy of trains across the route, which is covered by the CTC. The levers at the top is the lever for the switch, the electro-pneumatic lever for the switch. You can set the points to either use a particular siding or connect to the main line. And the levers at the bottom actually are the signals to clear the signals for that point, and it is interlocked. And here you will see a retired dispatcher actually explaining it. I won't cover the entire thing. You can just see it for some time, and then we'll move on to the next video. So as you can see here, the signal and the points have been set, and it's clear to move. So, and that's the same operation across the entire network. And moving on, this is the operation of CTC as it is today. And it's a very short video, but I think it makes sense to watch this video in its entirety. So I'll just take a pause here and let the video run. US runs on the right-hand side. So that's why it's called right. And if you remember, our Alcos also used to have seats on the wrong side. So ours is left-hand running. So that's essentially what the modern technology is doing here. And we would see that the advantages and benefits of the system in subsequent slides. So some of them have already been covered in the video, but we'll move on. So this is an example of a CTC board. Why I took it was in case for your train simulator fans, in addition to the train sim world, there is another train simulator called Run 8. Run 8 is a very authentic simulator. It allows for signal simulation, dispatching simulation, as well as complete running and operation of freight railroads in the US. So it's available on their website, and it's just an example from that game, a simulation game. So that's why I just thought this would be interesting for folks here. And then where did CTC help? So in some of you might be aware of this. It's the Southern Pacific Tehachapi loop. So loop line, single track line, a feat of engineering, but this is actually signaled using CTC. Okay. All right. What are the different scenarios and use cases and advantages of this? This is what was covered in some of the videos. So I did mention this. Single track itself can sometimes take over from two track absolute or automatic block system where there is only one directional running. If you have bidirectional running, 70% of capacity of two-track ABS can be taken. And some examples are there of US railroads doing this. And then you have double crossovers, two main track, which is also something that we saw. And then basically what this helps in is it increases the capacity of freight trains on the existing network. And then what it also helps is that if you have trains of different speeds, you have a slow running train, you have a semi-high speed train, you have a high speed train on an existing network, all the three can operate very effectively with minimum spacing between all the three. So that's the benefit of centralized traffic control. Okay. So we are done with CTC. So moving on to the newer technologies. So till this, we saw the 20th century. Sorry.
Mani, I hate to interrupt. We have crossed 40 minutes. So
Okay.
Please wind up in the next 10 minutes or so.
All right. All right. Sure, sir. Thank you. These are the newer technologies, and this is what is being done in the 21st century. So one is automatic train control. The second is Alstom Advanced Civil Speed Enforcement System, ACSES. And then the last one is what has been mandated recently in the US, which is positive train control. So positive train control is nothing but a combination of the automatic train control system, the civil speed enforcement system, plus GPS. So all this also ensures in a moving block rather than a fixed block, which is where we are going towards. Okay. Automatic train control. So this had its origins in the mechanical train stop. So if a signal was passed at danger, or if there were any other kinds of issues, there was a mechanical lever which tried to stop the train, and it was especially used on old school rapid transit systems. So that's where it came up from. And then now we have much more complex train control systems coming from automatic train stop. I'm sorry, I think we can go to the next slide. Yeah, from automatic train control, we move on to in-cab signaling. In-cab signaling is basically a replica of the signaling which is on the track side, which is provided to the driver. It not only provides signaling aspects nowadays, but it also provides multiple real-time information. And it's very important for semi-speed and high-speed lines. And in the US, you do need to have in-cab signaling and some form of automatic train control for speeds more than 79 miles per hour. So this particular slide tells you how an in-cab signaling works. So basically, you have at the left, you have a pulse code transmitter on the track side, and that generates pulses of different frequencies corresponding to the different signaling aspects. In the middle, you have the pulse code receiver on the locomotive, and then on the right-hand side, you can see what is there in the driver's cab, which gives the signal indications. And on the extreme right, this is what I was talking to you about. This is the civil speed enforcement system, which is used on the latest high-speed lines in the US. You have 9-aspect speed signaling, which is used by Amtrak. So this is the trackside pulse code generator. This is the pulse code receiver on the loco. This is the equipment on the cab. And of course, I spoke about what is being used at Amtrak. Next. The next is positive train control. So as I said, the combination of all these technologies, your CTC, your automatic train control, and your GPS combined together created what is known as the PTC. So basically, positive train control also tracks the train, the direction of train, and a much more granular tracking of the speed of the train. And then this has been mandated across multiple systems in the US. So you have some variations for the suburban railway network, the passenger railway network, as well as for the freight network. The architecture is given here. So you can see that in addition to the normal signaling equipment that I was talking about, with your automatic train control equipment, your wayside signals, and your in-cab signaling, you have a radio and a transponder, which provides a much more granular view of how the trains are run. And then there is a short video about it. I think we can skip the video. We'll just focus on the architecture. The same PTC is used by freight railroads with a GPS tracking technology. So this is the video by SEPTA. So SEPTA is Southeastern Pennsylvania Transit Authority. So they were one of the first to come up with this. So what's he trying to test here is that this particular positive train control, since it tracks the direction and speed of the train, it will also show you what speed the train driver, the loco pilot, has to operate. And then if he exceeds that speed, it will automatically reduce the speed up to the permitted speed. That's one thing. And then if there is a stop signal which should not be crossed, it will automatically apply the brakes so that the train comes to a stop within that well before that signal. I think some of this is also being adopted in our Kavach as well. Let me just show you that. So this is a modulated braking to bring it up to the stop signal, which is the second scenario which you saw here. This is the same SEPTA signaling in pictures. They are using a position light signaling, but it's a triangular position light signaling, which you can see on the left. Just quickly skim through this because it's basically the same. Right. So the freight railroads PTC system is somewhat similar, but it's a little simpler because you don't need the same number of aspects. You just need three elements. You need an onboard locomotive system, you need a wayside system, and then you need a back office server. And then the structure of a freight railroad PTC system is provided in this chart. So you have a base station, a signal switch, an operation center, and then a GPS which tracks the position of trains. So we will skip this video and then we'll go directly to this chart. Just an overview of what's happening on a freight railway system. All right, now we are done with positive train control. Then we move on to signaling for high speed. I think I'll take just 5 minutes about this and then I'll move on to what is the future, because I think people are aware of the Kavach here. We'll probably cover Kavach at a later point in time. In Germany, it is probably the most unique and advanced signaling system. It's called as LZB and PZB. And then it's extremely granular, and we'll cover what these two are. And then the French high-speed signaling is called as TBM 430. We won't be looking at the French signaling here because it's quite similar to, and it's and a much more granular operation is already covered in the German signaling. So what is PZB? PZB, as you can see, it's an unpronounceable German. Punktförmige Zug wie Inflation. It means spot-wise signaling, and it's an inductive protection approach. It's also called INDUS-E because it's inductive train protection. It's based on magnets, and it was introduced in 1934. They are using three magnets here, 500, 1000, and 2000 hertz. So these are the frequencies emitted by the magnets. So what the PZB does is that the driver has to acknowledge the frequency, and then he or she should try to reduce the speed up to a point. It doesn't exactly show to which speed he has to operate in, but it has to reduce up to a point. And if he doesn't reduce the speed appropriately, the brakes will be automatically applied. So it's pretty complex, but I'm just giving a very broad overview, and this is how it operates. In 1000, you acknowledge and you do the first speed reduction. If you don't acknowledge, again, brake application. In 500, speed is checked against a lower speed. And 2000, it's a main signal, you have to come to a full stop. And then I'll show you some images of PZB. So here, from an approach signal, the distance which they have to traverse and acknowledge and the overlap that you have for the stop. This is the same thing using a semaphore signal. When they first tried out PZB, you have the trackside magnets. This is attached to a tender of a steam locomotive. So we're just seeing that. This is the current Siemens magnet, which is currently being used on lines in Germany. What is attached to a Stadler multiple unit. And this is the braking curve that the Germans design when they set up signals. And what is important here is that the signal should also be set up and the distances should also be ensured that the speed and the deceleration works to the safety and also capacity. So that's how they also design their signals and the distances over here. So that's all about PZB. So the next technology which the Germans had is the LZB. That's the evolution of PZB. It's called Linien. which means linear. So this incorporates in-cab signaling, your automatic train protection and automatic train operation. They have a sort of cruise control for trains called AFB. So it once you set a speed, it automatically ensures that the driver need not move the throttle at all. So based on the trackside signaling, the throttle automatically reaches that particular speed. And then it also brakes as well once that AFB has been set up. And then you have automatic train protection. So this is extremely advanced. They have a version 2 also. And then with the European Union's ETCS, the European Train Control System, they will be merging this with the ETS system. And they are also using this LZB in conjunction with radio control, which is called FZB. So images of LZB. So you can see at the top left, these are the major sections of the high-speed German network with LZB. And then the middle image here, again, it talks about the deceleration curve, the speed and the deceleration and distance curve while they set up this equipment. And a much more detailed view of the equipment is in the bottom diagram. And then if you look at the faces here, the LZB operates through a cable loop, and then you have the interface on the German ICE train. That's essentially what I have given here. We'll just quickly skim through this because I also wanted to cover the future. Okay.
So finally, we are running out of time. Please come to the conclusion.
Sure. These are the 4 different kinds of signaling systems in Germany. Atulya, I might take maybe around 2 minutes and then we can close. And maybe we can go a little more in after 6 for the questions, if at all they have. Okay. Variable speed signaling. These are the 4 different kinds of variable speed signaling systems. And you can see here that these are all a variant of the American speed signaling systems. So this is the HI system. You have signal 2 is clear, and then clear with expecting 40 or 60 kilometers of the next signal and so on. So you can see that they are fine-tuning their signal. So likewise, you do have other kinds of signaling systems in Germany. This is the KS system with its aspects. And then this is a variant of the KS system, which is all clear aspect without any approach speeds in between. And then the current speed signaling system in Germany is called the SV system. So you can see that the signal 2 is clear, 4 is clear, expect medium speed. Signal 6 over here is medium speed, expect stop at reduced distance and stop. So they are fine-tuning it. And this is the current system. I mean, there are some differences in East and West Germany, as her Timo had covered earlier, but they are trying to standardize this. Okay, so we will skip this because I think we already covered bits and pieces of this. The coverage system is basically what we are trying to adopt. It's similar to the positive train control I had mentioned earlier. And these are the schematics of coverage. Basically uses a radio interface. You have a connection with the locomotive, and then you have a radio frequency tagging for the loco, which is being reached by receiver. And then you have the driver interface here, which gives the speed and the route signaling aspects and the speed which the driver has to take. I think this was what was tried on the Vande Bharat high-speed trials, which was being mentioned earlier. And then finally, we have some suggestions for the railway. So we can try to do, I mean, these are just my personal suggestions. I mean, if you want to increase the speed on the existing network, we can go for a signaling philosophy change with a much more granular aspect. And then we can try installation of CTCs across more sections of the Indian Railway network. We can implement in-cab signaling, and of course, a much more extensive use of Kavach to increase the speed and throughput on the existing lines in India, along with the dedicated freight corridor and high-speed railways we are having. So this can increase efficiency and speed on existing lines. So route to speed signaling, more aspects to signals, more CTC, install in-cab signaling, and then phased introduction of Kavach. And then finally, I come to the conclusion. The conclusion is complete automation. So you have grades of automation 0 to 4. So we are somewhere between 1 and 2 now. So going forward, it's all going to be driverless and unattended, with every aspect of it completely controlled, either automatically through a preset logic, or it can be done remotely by the driver operating from a very distant part of the world. So for example, you can see here that these are the different grades of automation from automation 1, 2, 3, and 4. And then automation 1 is nothing but shunting using cameras. Automation 2 is using LiDARs. Automation 3, which you can see here, is a driver operating a live train on a live track from a different location, like drones, with how you operate trains on simulators. And then finally, you have metros and rapid transit, which has full driverless operation. So that's the future. So with that, I conclude my presentation. I know it was pretty long and pretty complex, but I do hope that I gave a foretaste of signaling, an overview of signaling. And thank you very much for patiently listening to this. And I hope it actually increased your interest in this arcane topic. Thank you.
Thank you very much, Mani. It is indeed a very, very informative, a very well-researched and very well-presented presentation on signaling, right from the historical background to the present day and the future. There is a comment from Mr. Venu Mathur, the president of RES. He says, on Indian Railways, we had lower quadrant semaphore arm, multiple aspect upper quadrant semaphore signaling, and now multiple aspect color light signaling. We also had CTC on some sections on any railway. In my career, we have had mechanical interlocking to 3 different standards, route relay interlocking, and now electronic interlocking. We have many sections with automatic signaling, which may be somewhat different from the US. This was a thought in my mind also, that I have been working for Indian Railways for the last 37 years, but I had no idea of signaling beyond what we use on Indian Railways. And your presentation has been an eye-opener in that direction. We have one question from Nitisha. I just read it out. It's a very short question. She says, how was route taken care of in speed signaling system? On IR, there is a connection because a yellow signal can indicate that you're going to stop or you are going to enter the loop line. So there is a relationship between the color and the route as well as the speed. I don't know how, if you have entirely different systems, how do you reconcile these two things?
Okay. Sir, no signaling system is completely distinct, right? So I did say that in the US, they do follow something called as a speed signaling with a weak route signaling. So they do have on the same signal mast indications which actually indicate the route to be taken along with the speed. So that's how the route is taken care of in speed signaling systems in the US.
Thank you. Thank you. I think that covers the point raised. Then we have some very complimentary remarks by Mr. Hemkar Tata, Dr. Lalit Maudar, and Ashish Agarwal. So because we are short of time, I'm not reading out the remarks, but then I just wanted to convey that your presentation has been highly appreciated by all the listeners.
Thank you. Thank you very much, everyone.
Thank you. Thank you.
Thank you, Mani, for your excellent presentation. You have been a moderator as well as a presenter and done well in both accounts. Wonderful.
Thank you.